Hey, it's Mr. K doing a video for AP Physics C and Physics 1. It'll work for both. We're going to look at linearization today. It's a graphical technique that you will probably only learn in physics unless you took stats, AP stats. I think they teach it there. But for the most part, you usually don't run into this method until more of the science classes, because a lot of those weird numbers that we have, those constants on the equation and constant sheet, you get those by doing this technique, using data, putting it all together, and trying to find some relationship between them. And so we're going to take a look at this data here. So here you go. Down to the paper, we have our three kinematic formulas that we have derived thus far, and we have this set of data. We have a ball dropping. It is starting from rest. Still pretty simple of a problem. And here's the data. We have 0 seconds, 0 position. We fall for 2 seconds total. Final position of -20, and we will call this in meters, and we'll call this in seconds. And so if we were to take a look at this and graph it out, we're going to probably see an exponential curve. All right. So for instance, if I fall for 1 second, it's at -5 meters. If I fall for 2 seconds, we're at -20 meters. That's exponential. If it were linear, then if we fell for twice as long, it would be that same amount more, -10 meters, but we're at -20. So let's go ahead. I'm going to fast forward through this, graph it out, and we're going to take a little bit of a look at the graph here and what we can do with it. So fast forwarding. Okay, bring it back. We've got a rough sketch or rough plotting of points. Yes, you could use Excel to do this, but sometimes it's better to do it by hand. I want you to know how to do it by hand so that you're not as afraid of it. A lot of times students are very apprehensive towards graphing by hand because they just suck at it, honestly. And the way that you get better is to practice it. You just got to do it. So scale it out. I probably should have used a different scale down here based on the grid and only having 8 points of data, but my bad. But graph it out. I kind of estimated where these things were, and if you look, we do have an exponential curve. Take a straight edge. You can see that it is obviously not linear, not straight, and so we are increasing in slope as we go on. So one thing that we should probably do is we could do a smooth curve line to connect all these dots. Probably do it like this. Smooth curve line. And some of the dots will go over and below it, above and below it, but do your best to make a best estimate, kind of like a line of best fit, exponential line of best fit. Much easier to do a linear line of best fit, but it's not linear. Let's just talk about this for a second. So looking at this data, graphing out this data, we have a curve. What does this graph represent? That's position versus time. So as time goes on, there's more position being moved per time interval, which means, hey, we're getting faster. So looking at the graph, we can look at several things. One thing that we should look at is the rate of change, or the slope. And here, the rate of change is going to be a change of position over a change of time. And we know that to be velocity. All right, so the slope here is going to give us our velocity. It's only going to give us our velocity in the y direction. We don't have any information about the horizontal position, so let's not worry about it. Looking at this, to find the average velocity for this time interval, we could take the total change of position and divide that by the total time, and so you would look at something that looks like this. Now be careful, because a lot of times when you take the average velocity for something that is accelerating, your actual final velocity is not the average. You know, obviously, look at the slope. The slope of this green line matches more something in the middle-ish compared to the actual ending slope there, which is much steeper. So a big mistake that you might make is, you might actually find the average velocity for something when really you kind of need that final velocity. We need the instantaneous velocity by finding the tangent line. We talked about this in a previous video. If we wanted the instantaneous velocity at 1 second, let me use a different color, you would find a tangent line that would best fit for that specific point, that would only kind of come in and nick that one point. Okay, so whatever the slope of this purple line that I just drew, that would be the instantaneous velocity for that particular point at 1 second. Okay, if we looked at the velocity at the very end, the slope of this point would be the tangent line that runs through that point, like so. And if you were to find the slope of your tangent line here, then that slope should be, well, it should be the instantaneous velocity at that particular time. If I drew this well, then the slope right here at the 1 second mark should probably be about 10-ish. Because if you fall for 1 second, you go from 0 velocity to 10 meters per second. The slope at the very end here, the 2 second mark, should be a slope of about 20. So actually, let's just go ahead and see if I got that right. So here I can do a rise of, say, 5. I have a run of a little more than half a second. So 5 divided by about a little more than 0.5 is a little less than what I want it to be. But again, we are just approximating, so close enough. But that's not the point of this video. We're getting off topic. So the point of this video is to look at this process called linearization. So we have a curve data set. How can we turn a curved data set into a straight line? That's weird, right? That's not something that you're used to. And so the way that we're going to start off doing this, we're going to do this a lot, is we're going to look at an equation that might fit our data set. Sometimes you don't know the equation, and you're going to have to know what trend that data set follows. Like, is it exponential, like an x squared kind of exponential? Is it going to be logarithmic? Is it going to be kind of like a square root kind of thing? But here we kind of know equations of motion already, so we're going to apply one of the equations of motion to this data set. And you could just take these pieces of data and plug it straight into one of these equations and pop out something that you're looking for, like acceleration. But what if your data wasn't spot on? What if it was real data? This is fake data, just so I can get some numbers out there. We're going to do this in class, and you're going to use your data, and your data is not the best. And so how do we get around all that error that would be brought in by manual measurement? Even though we have video analysis, how could we take all that data you can get and kind of eliminate a lot of the error? That's linearization for you. That's what it's going to do. So let's take an equation, and let's take one equation that matches up with these two things, and let's try to find the acceleration of this problem. So all three of these equations have the acceleration. The first one, though, has time and the velocities, but it doesn't utilize our position. We want the equation that utilizes position. The second equation here utilizes position, but we don't utilize time, so let's use that third equation. The third equation, I'm going to write it down again over here, is the change of position is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. And so let me use a different color. So using the data that we have, we're going to manipulate this algebraically and then apply it. So what do we know? We know that we're dropping from rest. This is an easy problem, and if you drop from rest, the initial velocity is nothing. I want to find that acceleration, and just algebraic manipulation, move the 2 over, 2 delta y. I'm going to move the t squared over, divide by t squared, and that's equal to your acceleration. So if we knew the change of position, if we knew the time associated with that, you could find an acceleration. And using these numbers, it should get you an acceleration of about -10. It should. But let's not assume. Okay. So a lot of times, if you think you know the answer, a lot of your method will tend towards that, giving you that answer, and that's not great science. And so let's not assume that we already know the answer. We know how to check it, but let's assume that we don't know the answer yet. How could we get acceleration based off all these data values? And yes, you could plug in the first data set, the second data set, the third data set, and try to keep on going to get this acceleration, but it might be jumping all over the place. And so we're going to linearize to kind of get around that. And what I mean by linearize is that we need to modify what we have in this table to make it so that when we graph it again, it's a straight line. And so I want you to look at this equation. You see how t is squared? We're going to do that to every single t value in this column. You see how y has a 2 multiplied by it? We're going to multiply all these things by 2. And if we regraph those new modified values, we should be able to get a straight line. So let me go through. I'm going to fast forward through this part. I'm going to multiply the times by themselves, so square them, and I'm going to double all your positions. All right, so let's do that. Okay, coming back, we're still going to fast forward through the graphing portion, but yeah, kind of ran out of room there on the side to have another column. But all data has been modified, times have been squared, positions have been doubled, and then now let's get into the graphing of that. So fast forward again. Okay, so here we are. We've graphed it out. Had some camera issues in between, so let's see if I can edit those. But here we go. We have our data. We've graphed it again. We've linearized it. And to prove it, look at these data points. These are still estimated points, but look, that's pretty darn straight, right? So I'm going to go ahead and do a line of best fit, which is going to go through all these points if possible, some above, some below. And it just so happens to go through 0, 0, which is awesome. Sometimes it might not, and that's okay. But we just need to go by the data that we have. So looking at this, we got a linearized line. It's straight. How do we use that? Okay, and so now that we've linearized, we need to find the slope to this line. And the slope to this line, it's pretty much going from 0, 0 and to this point over here. So we go up 40. That's my rise, over 4. That's the run. Now that might seem like cheating, because you would be like, oh wait, Mr. K, don't we already have that over here? 40 and 4. You're just using the full big change, and that's true, but that's not always going to be the nice case. You know, what if it didn't go through 0, 0? You couldn't just say it goes up 40 and over 4. And so, you know, let's just for the heck of it, let's just use some random other point. So I'm going to say this point right here, and we're going to say we go up, that's 25, and this is going to be over about 2.5. Okay, and so the slope here, 40 divided by 4 is about 10. 25 divided by 2.5 is also about 10. That gives you the same slope. All right, so don't just pick the very end point unless you're coming from 0, 0. And only go through 0, 0 if your data says you should go through 0, 0. Here, yeah, it did. So we've got this slope of 10. And what did we find? The slope, remember, was a rise, which was 2 delta y divided by delta t squared. And that is A. And so we have just linearized and found the acceleration that we got on this falling rock due to gravity, and that's going to be about 10 meters per second squared. And the direction would be downwards because all these values here for position change should be negative. But I wanted to do it like how you would do a normal graph. So there you go. That's the video. We will stop here, and I will see about these camera cuts.